In this video, I'm going to do a quick proof about energy conservation with pendulums. So a pendulum is just, I'm sure most of you have seen it before, but just any object, think a clock, think like a string where you're swinging something back and forth. That's just, we're going to say it's a string with a negligible mass and that it's oscillating back and forth around some central point. And so in your sheet that I gave you for your PowerPoint, there's a equation that has to do with the maximum potential energy, and you do not have to be able to, you shouldn't have to memorize this, you should be able to show it on your own. So in our problems, we'll have some angle that the pendulum's swinging about, and this is always a small angle approximation. Calculus and beyond can help show why it's a small angle, but for us, we just need to know that all of our physics with pendulums only work if the angle is relatively small. And if we lift this to be some length, that means that we've given our pendulum, here, let me try a different color just so it can be different. We've given our pendulum some potential energy. Remember, the formula for potential energy is U equals mgh. Why did I write G first? I don't know. And I guess we wrote Y. I should do that for you guys too. And at the bottom, that potential energy, just like in the energy skate park from last semester at the end in December, at the bottom it has all kinetic energy, 1/2 mv squared. In the middle, between the top and the bottom, there's some kind of potential plus kinetic, and the total energy has to be conserved. But really, I just want to know, how could I write this height in terms of the length that I'm working with? So if I know that the string has some length L, that also means that when it's at the bottom of its path, it also has some length L. So I could kind of redraw this and say, okay, well, I have some length L, and then I have some other length L. This is not really to scale. I'll make it a little bit better. That looks a little more believable, maybe. And then I'm interested in the height difference between when I'm at the bottom point to being at the top. If I know that this is my angle, then I could solve for this side of the triangle. So I know the total side of the triangle is L, but I'm interested in what's the actual part that could connect and make a right angle. I could do that by connecting it with the cosine. I could say the cosine of that angle is going to be some height I don't know. I'm just going to call it x for now, over L. So I'm calling the green is L, and this is x. That means down here I could say x equals L cosine of the angle. So then I'm going to relabel this one more time. So I know that the whole length is L. I know that this part of the length, I'm trying to draw like a parallel line, is L cosine theta. So I could say, well, that x term plus my y term equals that term I called L. I could substitute and say L cosine theta plus y equals L, or y equals L minus L cosine theta. I can then plug that back in, and I know that when my energy is all potential, the amount of energy I have in terms of mass, gravity, and the length of the string is L minus L cosine theta. Now that I have this, I can do a lot of conservation of energy problems where maybe I'm going to say E initial equals E final. And I could maybe I want to figure out how fast it's going at the bottom or what the speed is at the top. hopefully that helps. Maybe some of you could do that without even using this video, but there's a little quick proof of that idea that was in the class kick.